Here we're going to introduce the concept of chemical potential, which is an important concept I'll be using throughout the rest of thermodynamics. Chemical potential. All right. Now remember, so far we said, it's around here somewhere, there it is. So far, for example, we said G, the Gibbs free energy, was a function of pressure and temperature. Now we also said in the previous lecture that in fact dG is less than or equal to dW prime, where this now was a non-PV work. See, if we just have G as a function of P and temperature, the only work that can be done is PV work. So now what we're going to introduce is a third variable that G is a function of, and that is number of molecules, or number of moles in. So free energy now will be explicit. G is a function not only of temperature and pressure, but also number of moles. Okay, so we'll start that. So let's go ahead and do that. G, because we're chemists and we're interested in number of moles and energy changes when we change number of moles of products and reactants, we now say that G is a function of not only pressure and temperature, but number of moles. And in general, this could be N sub I, where I is the ith compound in a reaction. So we could have N1, N2, N3 if we have A plus B goes to C. Okay, well, let's see what we can do with this. dG now is how G, let's do temperature first. Temperature at constant, now we have to have a constant pressure and number of moles because we have three variables times dt, plus how G changes with pressure, again at constant temperature and number of moles, two variables here, times dP, plus, and that new third variable, how G changes with number of moles at constant temperature and pressure times change in number of moles. Okay. We are going to give this a special symbol, and that special symbol will be defined as mu. So mu, Greek letter, lowercase mu, stands for chemical, or stands for how G changes with N at constant temperature and pressure, and this we'll call the chemical potential. All right. And we've already done the same for here. For instance, this we associate with a volume. No, with temperature, sorry. With temperature goes entropy minus S, and this we associate with volume. So let's put all these new symbols in, plus these old symbols, and we'll end up with this equation. Lecture8d, where'd that come from? There. Okay. So we'll just put a dG is minus S dt plus V dP. Now I'm going to rewrite this as the sum over I equal 1 to the number of compounds of the chemical potential of that compound times dNi. So there it is. This is called the master equation of chemical thermodynamics, or sometimes called fundamental. And it's chemical thermodynamics because now we're having number of moles in a chemical reaction. All right, so I just wanted to introduce that topic there, defining chemical potential as mu. And if you have like 3 or 4 different kinds of molecules in your system, each one will have a different chemical potential. Now, the chemical potential depends upon the number of moles. And for example, if you have a reactant going to products, then the chemical potential of those reactants will decrease as the reaction proceeds from reactants to products, because you just have fewer number of them. And the chemical potential of the products will increase as the reaction goes forward, since you're getting more of those. So chemical potential, think of it that way, the potential of chemicals to do chemical work, to participate in a chemical reaction. Okay, well, we'll use this equation later on in thermodynamics. Okay, so let's define partial molar quantities. Partial molar quantities is how some state variable or some state function changes with amount. For example, if you take the partial derivative of G in Gibbs free energy with respect to amount, or number of particles or moles or whatever, that is a partial molar quantity. So that's mu. For example, a partial molar volume will be how the volume changes with number of moles at constant temperature and all those other things. All right, so partial molar quantities. Now with that, one more point is this. All right, so at constant temperature and pressure, constant temperature, that goes away, constant pressure, that goes away, the Gibbs free energy change is just the sum over all the components in the system of their chemical potential times the change in the number of moles of that particular substance. All right. And equilibrium will be when dG is 0, or when these chemical potentials, you sum all these chemical potentials up, they'll be equal to 0. All right. Now, show that for an isothermal process, the partial molar volume, so if you have some quantity, say X, with a bar above it, that bar can be many things, but in this case, that bar means partial molar. So what you've done here is taken the derivative of X with respect to number of moles. So what we want to show is that the partial molar volume is how chemical potential changes with pressure at constant N and T. That's interesting. So if you measure the partial molar volume, see how volume changes with number of moles, then you have how chemical potential changes with pressure. Not something you'd think up immediately. All right, so let's show that. Let's say, as we said, now G, the Gibbs free energy, is now a function of both of number of moles in addition to pressure and temperature. We got that third variable in there. And, when we talked about Gibbs free energy, it was non-PV work. So that non-PV work, when we add number of moles, is chemical work. All right, so we now do what we did before, take the derivative with respect to the various parameters, and this is an isothermal process. So let's say constant temperature. So we don't have to worry about this. The only two things are changing is number of moles and pressure. So let's take the derivative of G with respect to number of moles at constant pressure and temperature, and then take the derivative of this with respect to pressure at constant number of moles and what else? Got temperature here. Now we have two things you have to hold constant because we have three variables. G is a function of three variables. So let's reverse the order. G is a state function, so we can reverse the order of differentiation. So this would be how G changes with pressure at constant number of moles and say isothermal temperature, and then take the derivative of that with respect to number of moles at constant pressure and temperature. All right, so this we've defined as the chemical potential. And this, remember how G changes with pressure, constant N or T. You can go look that up, but in fact what that is volume, the conjugate variable that goes with pressure. All right, so just write this, how mu changes with P at constant N and T is how volume changes with N at constant P and T, and this is defined as the partial molar volume, how volume changes with the number of moles. That's just partial molar volume. So it looks like we've shown that partial molar volume is how mu changes with P at constant N and T. All right, so that's it for Lecture 8. We'll develop the idea of Gibbs free energy and start moving into chemistry in the next couple of lectures. Thanks for listening. Have a nice evening.